Hi guys, I'm Sanjeevi of AI department. Today we are gonna see about Nd-YAG laser processing in ceramic industries session. Laser drilling of aluminum ceramics using solid state Nd-YAG laser and CQW. Fiber laser effect of process parameters on the whole geometry. Introduction. Technical ceramics such as Al2O3 can be found in many fields of human activity. It is used, for example, in microelectronics as thin film substance in circuit boards, in automobile engines, telecommunications, or mechanical engineering for producing valves, seals, and pump impellers. Significant explosion of ceramic is also an medicine and orthopedic implements are made from it. Due to its characteristic properties like high hardness and brittleness, high thermal conductivity and wear, and chemical resistance, it's hard to machine it by conventional methods. Fortunately, laser machine brings several advantages including high precision and process control together, which a reduction of mechanical stress. Moreover, laser treatment ensures low heat input to the material, thus the heat affected zone around the interaction area is limited. Laser machine ceramics is actually used for many applications including cutting, drilling and scrubbing. Lots of laser parameters, mainly pulse, length, peak power, pulse energy, pulse frequency, and focus positions, are involved in laser drilling. The previous papers are mostly devoted to the study of the effect of laser parameters on the drilled holes and their characteristics. Involving taper, recast, spatter, and microcracks for every specific application, it's important to find the optimum parameters to achieve required hole geometry and quality. For example, Cibology et al. 2011 studied the process of Nd-YAG laser drilling of Ni based superology Mnemonic 263 seeds and developed a hybrid strategy that is able to find optimum parameters and fulfill the specific demands for seven characteristics of the drilled holes including holes diameter, circularity, aspect ratio, taper and spatter. In literature, there are reports that concern experimental and theoretical investigations of the laser drilling processing of aluminum ceramics. Carker et al. 2009 inspected the dependence of the hole diameter on the laser peak power using Nd-YAG laser. The ascertained that the hole diameter increased with peak power. Nadialkov et al. 2003 compared the process of ceramic drilling using fundamental, second and third harmonics of Nd-YAG laser experimentally and theoretically. Another theoretical model for predicting the hole circularity was presented in Bharadish et al. 2013. Examined and simulated the influence of laser parameters and geometrical and microstructural hole properties. They also compared the experimental and simulation results to access the difference in the hole dimensions. The first laser source was lamp pumped Nd-YAG laser emitted at wavelength of 1064 nm. We can obtain laser spots in focus plane 0.6 mm allowing maximum power 150 watt. Firstly fixed parameters during the process were frequency 20 Hz and pulse length 0.5 ms. The pulse energy in the range 0.7 to 2.7 Joule was adjusted by setting the flash lamp charge voltage. To investigate the effect of pulse energy on the hole's geometry, simultaneously the dependence on the number of pulses was examined as well. During the second experiment, the effect of pulse length, pulse energy, and the number of pulses was tested. The second layer was QCW ATBM fiber laser. with a multi-mode core fiber that can work at pulse mode providing various pulse lengths and high peak powers, as well as the continuous wave mode providing high average powers. QCW mode was used for drilling enabling and maximum peak power of 1.5 kilowatt. High beam quality and small spot size allow achieving high power densities for precise process. During drilling, the pulse frequency Cy was set to 50 Hz, and the influence of pulse length with the increment and the pulse energy on the whole characteristics were evaluated. For experimental studies, alumina ceramic plates with thickness 2 mm were used. Before starting experiments, the sample surface was cleaned by acetone to remove oil and dust reduced. Tests were performed at ambient temperature in air with the acid of compressed air supplied at pressure of 2 hours. Holes diameters and depths were measured with the help of scanning cochlear microscope. Olympus Lext 3100 measurements of dimension and 3 reconstructions of irritated surfaces were provided by attached software. Resultant discussions. Laser drilling is a complex process dependent on several laser parameters. Therefore, could be problems with melt produced during the drilling. Shape of the hole is affected by melt expulsion, and irregular incomplete expulsion causes formation of recast layer and can even close the hole. In this paper, modifications of hole geometries and analyzed under several process conditions. The effect of the wavelength, pulse energy, pulse length, pulse power, and number of pulse on the hole's characteristics were investigated. Ceramic drilling using Nd-YAG laser. Dependence of the entrance hole diameter drilled in alumina ceramics on the pulse energy for three selected number of pulses presented in figure 1. As one can see, the entrance hole diameter increases with the increasing value of pulse energy. The lowest value of pulse energy capable machine holding through the entire sample thickness 1.4 joules. For lower values, as interaction between laser radiation and aluminum ceramic surface was not observed. The graph also shows that number of pulses is not decisive parameter, as its influence on the diameter was not significantly proved in the contrast with Hannon, who claimed that the proportions of the hole were strictly influenced by the number of pulses. The recast layer produced after resolidification of the melt phase formed during the drill enforced the hole. Furthermore, a part of melt material can be observed also on the edges the exhibit hole created by low number of pulses. Okay. Ceramic drilling using QCW fiber laser. QCW fiber laser was the second laser used to drill alumina ceramics. The hole diameter was investigated in the dependence of pulse energy, peak power, pulse length, and number of pulses. The dependence of the hole diameter on pulse length is depicted in this figure. It's evident that the hole diameter is the lowest for pulse length 0.8 ms. The figure also shows that the hole diameter goes up with increasing peak power for each pulse length. In order to get more information about the holes, the entrance exit diameters are examined in the dependence on pulse energy. It was observed that the exit diameter increased with increasing pulse energy, although it was always smaller than the entrance one. Furthermore, a rise of entrance diameter is detected with increasing pulse energy for each analyzed pulse length. Thus, using the different parameters, it's possible to create holes with entrance diameters in the range from 133 to 266. Images of the entrance and exit holes drilled by laser radiation with pulse length 0.6 ms and 1 ms are displayed in this figure. Each figure is specific for certain pulse length and increasing series of peak powers. The entrance holes are quite circular, but a small amount of melt visible around the holes. On the contrary, the exit holes and melt is evident there too. Entrance and exit hole circularity can be improved using the higher peak powers as they deliver high energy radiation that transport the melted material further from the hole and does not allow its accumulated. It can be said that amount of melt present at the edges of entrance and exit holes is lower than high peak power too, since increase in the laser power leads to increase in thermal energy which costs better material by bias and Bharatish. Therefore, according to these statements, our observation high peak powers least 1 kilowatt are adequate for alumina drilling by fiber laser. In addition, amount of melt is reduced for shorter pulse. So pulse 0.5 ms and 0.6 ms optimum pulse length. For example, NG and LI suggested that the whole circularity was the best when drilling was performed at shorter pulse length and high peak power. Conclusion. In this paper, drilling of 2 mm thick alumina ceramics was studied in dependence on laser wavelength, pulse energy, peak power, number of pulses. The process was performed using Nd-YAG laser and QZW laser. The laser drill holes characteristics were analyzed and the influence of process parameters was determined. Created holes and their geometry was observed and evaluated using scanning confocal microscope. Drops of melt are visible at the edges of the exit holes as a result of incomplete ejection of the material from the cavity, which remains attached to the hole margins. Analysis of the hole reveals that the entrance diameter was always longer than the exit, thus, holes were positively trapped. The entrance holes were also wider than the laser spot diameter. The results show that it is possible to control the hole dimensions by changing the lasers and its parameters. Was possible to create holes with diameters in the range of 350 to 600 using Nd-YAG laser and form 133 to 266 using fiber laser. It's obvious that the fiber laser ensures formation of a narrow hole due to its small spot and better beam quality together with high power and energy densities. The hole diameter can also control by setting the laser parameters, example pulse length, energy and peak power. Both entrance and exit hole diameters go up proportionally with the pulse length and pulse energy. For Nd-YAG laser, circularity and less amount of draws was obtained and higher energies with corresponding energy densities around 1 kilojoule per centimeter, leading to the formation of hole with better quality using the parameters. We can also conclude the bigger number of pulses ensures getting better hole circularity. On the other hand, for fiber laser, it was detected that relatively shorter pulses, high peak power and high energy densities. Thank you guys. Let's end up the session and don't forget to subscribe our channel. And it's me Sanjeevi. Will meet on the next video. Until tata, bye bye. Good luck. Love you all.